Good evening, everyone. Welcome to the problem solving session of NPTEL Basic Electrical Engineering course. This is the week 10th of this course, and today we will be practicing some problems based on week 10th content material, that is time varying inputs to first order system. So, let's start. So, it is an interactive course. It is an interactive session. I will suggest you, those of you who have joined it, to try to solve the questions along uh, all along, so that you can get the maximum benefit from these sessions. So the first question is: you have been given a circuit uh, with a negative feedback op amp, and this op amp is connected in non-inverting amplifier configuration. You have a low pass filter at the input of this amplifier, and a low pass filter at the output of this amplifier. So it has been told that the input is 1 volt for t less than 0, and at t equal to 0 it switches off with a step to 0 volts, and the output is of this form, that is v1 e to the power minus t by tau 1 plus v2 into e to the power minus t by tau 2. So you need to figure out what are v1, v2, tau 1 and tau 2, where this part is the forced response, and this part is the natural response. So let's try this out. Now let's first focus on the first part of the first LPF of the circuit, that is at the input of the amplifier. So here what you see is, suppose this V1 is there at the input. So like what this circuit is basically like, for t less than 0, you have 1 volt voltage at the capacitor, because for a long time, since 1 volt has been applied across this LPF, so low pass filter. So no voltage will be developed across this resistor. All the voltage will come across the capacitor. So the V out 1 is 1 volt at t equal to 0, and after that, the capacitor will start discharging through this 1 kilo ohm resistor. So the time constant, since this is a first order circuit, so the time constant will be tau, that is 10 to the power RC, that is 10 to the power 3 into 10 to the power minus 6. So the total time constant comes out to be 10 to the power minus 3. Now, now this V out 1 will follow a first order decay. So it will be V of 0 into e to the power minus t by RC, and V of 0 is 1, and t by RC is 10 to the power minus 3. Now the output of the op amp will be the gain of this non-inverting amplifier multiplied by whatever input we are getting. So input is a decaying exponential, and that will be multiplied with the gain of this amplifier. That is, so for a non-inverting configuration, the gain is 1 plus RF by R1, where RF is the feedback resistor and R1 is the resistor at the input resistor at the negative terminal of the op amp. So from there you get the value of gain as 1 plus 3 by 1, that is 4. So at the output of the op amp, the voltage is 4 into e to the power minus t by RC, that is 10 to the power minus 3. Now after this, this output of the op amp goes to the second low pass filter. So that has R as 1.5 kilo ohms, and capacitance value as 1 microfarad. And for the now, since the output of the op amp is a decaying exponential, so for this decaying exponential as an input to this low pass filter, you need to find out V out 2. So we will try to solve it in both time domain as well as in Laplace domain, and compare the results. So in time domain, we have the following equation of different. It's a first order differential equation with respect to time for V out 2. That is RC into dV out 2 by dt plus V out 2 is equal to VOP. So this derivation has been discussed several times before. So Now, the RC product for this LPF is 10 to the power 1.5 into 10 to the power minus 3. And that if we substitute over here, this is what we get. That is 1.5 into 10 to the power minus 3 into dV out 2 by dt plus V out 2 is equal to, now VOP is 4 into e to the power minus t by 10 to the power minus 3. That is uh, that has come from the previous calculation. Now, this first order differential equation will contain a complementary function and a particular integral. So the complementary function is the property of the system itself. It doesn't depends on the input. So for that, you need to consider input as zero. Now, to solve the complementary function, what do you do? Complementary function can be solved as you consider the differential equation as a polynomial in, let's say, D. So let's say you have something of this kind, a polynomial in D where m varies from 0 to n, that is the order of the system. Sorry, 0 to n, that is the order of the system, that you equate to 0. And from there, you find the value, the roots of D. And from there, the complementary function comes out to be, so whatever roots you find out, some dk into e to the power, some coefficient ck into e to the power minus whatever roots you find out. So let's call dk into t. So this ck is a general constant that you need to find out based on the given initial condition and final conditions of the various initial conditions of various derivatives of the system. So let's try it out. Now the complementary function, so here the polynomial, the auxiliary equation that you get is d into 1.5 into 10 to the power minus 3 plus 1 equal to 0. So this is the auxiliary equation, and solving this auxiliary equation, the root you get as minus 1 by 1.5 into 10 to the power minus 3. So from there, and this is the complementary function that you get. Since it's a first order system, so it has only one root. So c into e to the power minus t by 1.5 into e to the power minus 3 into 10 to the power minus 3. Now the particular integral, so for exponential type of input, for an exponential type of input, the particular integral you need to find out by replacing d, the coefficient of the particular integral you need to find out by replacing d by whatever coefficient you have of the time in the exponential. So in this case, that coefficient is minus 1 upon 10 to the power minus 3. That is the time constant of the previous LPF. That was at the input of the non-inverting amplifier. So you replace d by this, and from there you get the value of particular integral as minus 8 into e to the power minus t upon 10 to the power minus 3. Now this is the forced response of the system. Now this response depends on what input you are providing, because so for this particular system, the input that you are providing as an exponential with time constant of 10 to the power minus 3. So the particular integral has a time constant of 10 to the power minus 3. So the final V out 2 comes out to be C into e to the power minus t by 1.5 into 10 to the power minus 3. Now this is the time constant of the output LPF, and the particular integral, that is minus of 8 into e to the power minus t by 10 to the power minus 3. Now the now you need to find the value of C. So to find the value of C, you need to look at the initial condition. So initially at t equal to 0 minus, you see that the output V out 1 is equal to 1. It is mentioned in the question. So if V out 1 is equal to 1 and the gain of this amplifier is 4, so VOP will be 4 volts, and the same will come out at V out 2 also, because in steady state the resistor can be considered as a short circuit. So having said that, uh, the VO2 is equal to 4 volts. So at t equal to 0, these two exponential go to 1. And from there we get 4 equal to C minus 8, C equal to 12. So the final answer that we get is 12 into e to the power minus t by 1.5 milliseconds minus 8 into 10 to the power minus t by 1 milliseconds. So the this part is the forced response, and this part is the complementary function, that is the natural response. Now the same thing you can do in, so this was a tedious process. Let's see how to do it in time Laplace domain. So in Laplace domain, you know that uh, the impedance of a capacitor is 1 by SC, where C is the value of the capacitance. So from there, now here you can apply the resistive divider. So a resistive divider is basically ZC upon ZR plus ZC, where ZC is the impedance of the capacitance and ZR is the impedance of the resistance. So from there you get the relationship between input and output as Vs upon 1 plus S times Rc. So now Vs is the inverse Laplace transform of, Vs is the Laplace transform of the input, that is 4 into e to the power minus t by tau. So that comes out to be 4 upon S plus 1 by tau 1. So the final output that you get is 4 into tau 1 upon S tau 1 plus 1 plus SRC plus 1. Now RC is the R and C product of the output LPF. So substituting the value, you get this. But you get substituting the value, you get this equation, this rational function in terms of S. So that can be broken down into partial fractions. Now rule for partial fraction is, let's say you have 1 upon S plus A into S plus B, that can be broken into A upon S plus A, capital A upon S plus small a plus capital B upon S plus small b, where capital A is equal to 1 upon B minus A. So basically you put the root of one of the factors as S in rest of the other factors, and accordingly you calculate. So basically from the residue theory, so A is equal to 1 upon B minus A, and capital B is equal to 1 upon small a minus small b. So using this principle, we find out the values of coefficients in partial fractions. And from there, we know that inverse Laplace transform of 1 upon S plus A is equal to e to the power minus at u of t. So from there, you get the values of value of V naught as 4 into 10 to the power minus 3 into this thing. So if you simply simplify it, you get the same value as you calculated in the time domain. So here is the time domain equation. So this is how you needed to find it, both in Laplace domain and time domain. And Laplace domain is a quicker solution, provided that you don't have any initial conditions. In case of initial conditions, we will see in later questions what we have to do. So now this is a question with the initial conditions. So we will solve it with Laplace transform. So let's see over here. So what is given is that, so it is cos omega t u of t. That is a sinusoid that is applied at t equal to 0, where u of t is a unit step function. So to this network of this RL network, input of cos omega 5 cos omega t u of t is applied at t equal to 0. And initially, just before the application of this input, the initial condition of the inductor current is given as 2 milliamps. So after t equal to 0, you need to find out the response of this complete equation. So that is of this form. It will contain a sinusoidal, response and an exponential response, you need to find out the total response. So what can be done in this case is initial conditions can be considered as a separate input, and actual input can be considered as a separate input, and superposition can be applied because the circuit is linear. But the initial condition makes it incrementally linear. But if you consider that also as a separate input, so you can apply superposition. So let's consider when no input is applied, that is, there is a short circuit in this branch. In that case, you will get the following circuit. So you have a 2 kilo ohm, 2 kilo ohm are comes out to be in parallel comes out to be 1 kilo ohm resistor. So this 1 kilo ohm resistor in parallel to an inductor with an initial current. So the current of this inductor, so basically the flux of the inductor will discharge through the resistor, and the discharging so I and the voltage developed across this inductor will be I minus of IL times R. So minus of IL times 1 kilo ohm, and IL, and since this is a first order equation, so IL will undergo exponential decay. So that comes out to be, so now the initial current is given as 2 milliamps. So the VL comes out to be IL times R, that is 1 kilo ohm. So minus of 2 into e to the power minus t upon 10 to the power minus 3, where 10 to the power minus 3 is the time constant. So the time constant of the circuit is L by R, and that comes out to be 1 Henry upon 10 kilo ohm, that is 10 to the power minus 3. So this is the time constant. So now this response you have found out for the initial condition. Now we will find out the response for the input, and then we will add the two to find out the total response. So let's find out the response for input now. Now, in case of the input, this is how the circuit will look. You have a V of S input and RL resistor divider. Now, the impedance of the inductor is equal to S times L, where L is the value of the inductor. So, from there, the output you get as, so the resistor divider between R and SL, and that comes out to be S into L by R upon 1 plus S into L by R, where L by R is the time constant. So that can be written over here. So, and V of S has been, V of S is given in the question as 5 cos omega t. Now, another important Laplace transform pair that you need to keep in mind is of we have the cos omega t is f upon f square plus omega square, and sine omega t Laplace transform is omega upon s square plus omega square. So having said that, the Laplace transform of the input comes out to be 5 times s upon s square plus omega square. So the final output comes out to be 5s square tau. So this also contained an s. The natural response, the transfer function of the system also contained an s, as well as the input also contained an s. So it becomes s square. So 5s square tau upon 1 plus s tau into s square plus omega square, where 1 plus s tau is due to the transfer function of the RL circuit, and s square plus omega square is due to the cosine input. So now what can be done is, now this uh, denominator again can be broken down into partial fractions. So partial fractions will be of the form a upon 1 plus s tau plus bs plus c upon s square plus omega square. For second order denominator, you have numerator as bs plus c. So from there, equating the actual numerator with the numerator of the partial fraction, you get 5s square tau is equal to S square into A plus B tau plus B in B plus C tau times S plus A omega square plus C. So what I've done is just recombined it as some n of S upon 1 plus S tau into S square plus omega square. And this n of S comes out to be what is written in the RHS. So equating the coefficients of S, the powers of S, you get these three equations. That is A plus B tau is equal to 5 tau, B plus C tau is equal to 0, and A omega square plus C is equal to 0. So from these three equations, you can find the value of A, B, and C. So A comes out to be 5 tau upon 1 plus omega square tau square. B comes out to be 5 omega square tau square upon 1 plus omega square tau square. And C comes out to be minus 5 omega square tau upon 1 plus omega square tau square. So now again, the Laplace transform is written as A upon 1 plus S tau plus Bs upon S square plus omega square plus C upon S square plus omega square. So C upon S square plus omega square will correspond to sine, and Bs plus S square by omega square will correspond to cos. So from that, this is the time domain equation that you get. That is 5 upon omega square plus tau square into e to the power minus t by tau plus 5 omega square tau square. So here the values of A, B, C are substituted. So from there you get these coefficients of exponential, sine, and cosine and sine. Now omega is given as 10 to the power 3 radians, and tau we have calculated as 10 to the power minus 3 seconds. So from there you get omega times tau is equal to 1. Now if you substitute this in the equation above, you get the value, the time domain for time domain expression of the output for cosine input is as 5 by 2 into e to the power minus tau minus t by tau plus 5 by 2 into cos omega t minus sine omega t. Now, from the trigonometric result, we have a cos theta plus b sin theta is equal to root under a square plus b square plus cos theta into tan inverse b by a. So the value of a in our case is 1 and b in our case is minus 1. So substituting these values, we get the overall. Root under a square plus b square comes out to be root of 2 for us, and b by a is minus 1. So so it was 5 by 2 into root 2. Now root 2 can be cancelled. So the final expression is 5 by root 2 of the amplitude, and the phase is tan inverse of minus 1, that is minus 45 degrees. So this is the final expression that comes out for cosinusoidal input, cosine input with an amplitude of 5 and frequency of 10 to the power 3. Now we add the initial condition output and the output due to cosine. So from there we get the final expression as 3.53 cos 10 to the power 3t minus 45 degrees plus 0.5 times e to the power minus 10 by minus t by 10 to the power minus 3. So after a very long time, you can see this exponential will have gone to 0, and what will remain is only the steady state output. So steady state outputs basically can be calculated from frequency response. So there you replace S by j omega in the transfer function that we have calculated, and for let's say cos omega naught t input, the output you get as magnitude of the frequency response at omega naught times cos omega naught t plus the phase is the phase response of the frequency response at that particular frequency. So with this concept, we'll solve one more question. So in this case, now you need to find out this is in the previous question you would have seen. So I explicitly mentioned that u of t was there with the uh, input. So that meant that the sinusoidal was applied at t equal to 0. Now, in this case, infinitely long sinusoidal has been applied to the circuit given, and in this case you need to find out the output. So if the sinusoidal that is applied has been applied long back, that is at some t equal to minus infinity, so the transient of the circuit has died down, and after that whatever remains is the frequency response of the system. So in this case, the impedance of the capacitor will be 1 upon j omega c. So you have this is basically S has been replaced as 1 upon j omega. J omega S has been replaced by j omega. So from there you calculate. So resistive divider between the the voltage divider between the resistive impedance and the capacitive impedance, that comes out to be 1 upon j omega RC plus 1 times the input. Now the magnitude of this input is 1 upon root under real part square plus imaginary part square, that is 1 upon 1 upon root under 1 plus omega square RC square. So that comes out to be, and RC's value is omega in this case is 10 to the power 6, and RC in this case is 10 to the power minus 6. So omega times RC comes as 1. So your magnitude response comes out to be 1 by root 2, and the phase response similarly comes out as minus of tan inverse omega RC, and that comes out as minus 45 degrees. So from there you get the value of this uh, the output in time domain as root 2 into 1 by root 2 cos 10 to the power 6 t minus 45 degrees. Now, you notice over here, this is a low pass filter. For omega equal to 0, the magnitude would have been 1, and for omega equal to infinite, the magnitude would have been 0. So what this system will do, this will behave as follows. So it will pass the very low frequency input completely, and it will stop the very high frequency input, and there will be some there will be this 1 by RC input, at which the voltage will drop to 1 by root 2 of uh, what the input is, and this is called the 3 dB bandwidth. So 3 dB comes as if you represent this represent this magnitude response in dB. 20 log 10 of 1 by root 2 comes out as 3 dB minus 3 dB. So this is called the minus 3 dB bandwidth of the circuit, and that is basically the reciprocal of the time domain, reciprocal of the time constant of an RC circuit. Now let's move to the next question. Now in this case, again, you need to find out the force response for the system, and now here what you have is, so again, so it is R1 upon the impedances of the capacitances can be written as 1 upon j omega c. So from there, what you get is the capacitance are replaced as follows. So the impedances of these two sections are Z1 is R1 upon 1 plus j omega C1 R1, and Z2 is R2 upon 1 plus j omega C2 R2. So in this case, the overall V out, if you find out through capacitive division, you get as R1 plus R2 into 1 plus j omega C1 R1 plus divided by 1 plus j omega C1 plus C2 into R1 R2 upon R1 plus R2. Now, there has been specific values of these R1, R2, and C2 being given. So it's mentioned that R1 is equal to 4R2 and C1 is equal to C2 by 4. So if you try to put the values, you get the following equation of the transfer function, that is 1 plus j omega R1 C1 divided by 1 plus j omega 5 C1 times R1 by 5. So these 5 are removed from numerator and denominator, and ultimately what you get is the pole and zero cancel each other, and you have an all path system. Now, so in this kind of system, if such values of resistances and capacitance are chosen in such a way such that R1 is equal to some alpha times R2 and C1 is equal to some C2 by alpha, in this case you get an all pass system. So this just behaves as a simple resistor divider of R2 upon R1 plus R2. There is no phase shift. There is only some magnitude drop due to the only the magnitude changes. So the final output you get as 5 into 1 by 5. So there won't be any transient in this particular case. There won't be any transient. However, had there been uh, this condition had not been given, in that case you would have seen transient also. But in this case, since it becomes an all pass system, so you don't see any transient. All pass system with no phase shift. Basically, there are all pass system with phase shift. So in that case, you will see the transient. But if there is an all pass system without any phase shift, you won't see any transient. Now, next question. So in this question, it has been given that an input is applied to uh, some system, that sinusoidal input, and it is asked that if R tends to infinity, then what will be the value of the output. So now if R tends to infinity, what happens is what you get is a simple capacitor divider. Now, if you even if you replace it, let's say by 1 by SC and 1 by SC, so what you get as the transfer function is 1 by SC, SC2 and C1, let's call this 1 by SC2 divided by 1 by SC1 plus 1 by SC2. You get as transfer function. So this boils down to C1 upon C1 plus C2. Now in this case, both C1 and C2 have been given as 1. So the final transfer function is half. So if 5 sine omega t has been given as the input, the output you get as 2.5 sine omega t without any phase shift. Now, again, you have been given a RC. So this is a different circuit than the ones that have been different that have been discussed before. So in this circuit, you see the the capacitor is in the input arm, and the resistor is at the output arm. So in this case, it has been given that VC of 0. The initial condition has been given as 1 volt, and the input has been given as 2 into exponential of minus t by 1.1 microseconds. So output you need to find out again in form of forced response and natural response. So let's try to solve it. So first we will find the uh, we will find only the response due to initial condition. So that will be basically we'll short the input, and we will have a 2 nanofarad of resistor. So in this case, the voltage across resistor and voltage across capacitor will be the same. So now this is called VC. So V out is equal to minus of VC. And since this is a first order circuit, so there will be a first order decay that will be minus of VC of 0 minus into e to the power minus t by RC. So this is minus of e to the power minus t by, now RC over here is 2 into 10 to the power minus 9 minus 9 into 10 to the power 3, that is equal to 2 microseconds. So minus of e into so minus of e raised to the power minus of t by 2 microseconds is the response due to initial condition. Now we find the response due to the input. So again, the input in this case is an exponential, that is 2 into e to the power minus t upon 1 microseconds, that is there on this circuit. So the transfer function from input to the output in this case is V out by V in is equal to, so let's call this, this can be replaced by its impedance 1 by SC, and the resistance is R. So it's SC.
I didn't catch that. Could you try again? One second.
So 2 upon S plus 1 microseconds. So the overall output that you get is V out can be written as S upon 1 plus S by 1 microseconds. Sorry, S plus 1 by 1 microseconds and S plus 1 by 2 microseconds. So this is the way you can write the output. Again, expanding it into partial fractions, you get the value as A upon S plus 1 by 1 microseconds plus B upon S plus 1 by 2 microseconds. So in this case, now the value of A and B you can calculate as discussed earlier. So A comes out to be 1 upon. Now here you have to put the value of minus of, so for that you will substitute. So this will come out as S upon S plus 1 by 2 microseconds, for S is equal to minus of 1 by 1 microsecond. So if you put that in this equation, you get value of A as minus of 1 by 1 micro divided by 1 by 2 micro. Sorry, minus of 1 by 2 micro. So this comes out to be minus of 2. Similarly, B comes out to be, so minus of 1 by 2 divided by 1 minus 1 by 2, that is, sorry, this is plus of plus 2, and minus of 1 by 2 into 1 upon 1 minus 1 by 2, and this is minus 1. Okay, so from here we get value of V out as 2 into e to the power minus t by, so I have directly taken its Laplace transform as e to the power minus at. So t into 1 micro minus of e to the power minus t upon 2 micro. So this is what you get as the expression for the force, the input only. So at the end, you can combine the expression for input and expression for final expression for initial conditions. So now initial conditions expression we have found out to be minus of e to the power minus t by 2. So at the end you get v out final as 2 into e to the power minus t by 1 micro minus of 3 into e to the power, sorry, so this is also minus 2, minus of 2 into e to the power minus t by 2 micro. So this is the final expression that you get for the output. Now the second part of this, let's copy this. Now in the second part, what we have is, you notice is that the expression for, so the input also have the same time constant as the as that of this thing, as that of the as that of the output, as that of the system. So in this case, what you will have is an expression of, so earlier you saw that if there the time constants of the input and the system are different, in that case you have something like c1 into e to the power minus t by tau 1 plus C2 into e to the power minus t by tau 2. But in this case, the system and the input have same time constant. So in this case, your expression of the output will be of this form: C2, C1 plus C2 into e to the power minus t by tau into e to the power minus t by tau. So using the similar approach, this can be solved, and the values of C1 and C2 can be found out. So uh, this was it from my side for this tutorial. Thank you for attending.